Hi everyone, welcome to Earth and Space Science 101. This is our very first lecture, so I want to welcome you to this class. My name is Stephanie Welch. I am an instructor of Earth Science in the Department of Chemistry and Physics in the College of Science and Technology here on campus at Southeastern. If this is your very first telecourse, or even if it's not, it's definitely worth your time to look through all of the materials available to you through Moodle. I've got lots of great stuff in there, and really all of it is designed to help you get as much as possible out of this class. In particular, you want to start the class by looking through the syllabus, the class schedule, which is going to be very important, the technical advice, and all of the study advice. That can all be found in the Course Information tab in Moodle. So the best way to get in touch with me outside of our regular class meetings, which will be once a week, is going to be through email. And my email is available through Moodle. So you can contact me through Moodle or you can send me an email directly. So in this class, in Earth and Space Science 101, we mainly cover geology and oceanography, with more of an emphasis on geology than the oceanography. That's going to be a fairly small part of it that we'll get into a little later on in the semester. So you might see the space part of Earth and Space Science sort of missing from 101. We cover that in the next class, Earth and Space Science 102, which is meteorology and astronomy. So in ESSC 101, the first thing I wanted to do was to kind of give you an idea of all of the topics that we'll cover this semester. You can find this in a little bit more detail in the syllabus and in the textbook, of course, but I kind of just wanted to give you sort of like a basic structure of what we're going to cover in each of the units. There will be 4 units overall, each culminating in a big unit exam. And we'll cover in Unit 1 the broad subject of plate tectonics. It's basically the underlying driving force for most of the uplift forces in geology. So as part of the plate tectonics segment, we'll cover plate boundaries, plate tectonics theory, we'll cover geologic structures like faults and folds, earthquakes, the Earth's interior, and mountain building. In the second unit in this class, we're going to cover rocks and minerals. So that's some basic chemistry, elements and bonding, mineral properties, and all of the different types of rocks, including igneous, metamorphic, and sedimentary rocks. In the third unit in this class, we're going to cover water on Earth. And that subject is going to bring us really sort of back to Louisiana, and that's where I can cover some of the most interesting local geology we have, which is all basically going to be related to water. So we're going to cover the water cycle, the importance of the oceans, coastline processes. We'll cover oil and gas as part of that unit, and I'll kind of explain how that fits in a little bit later. We'll cover rivers, especially the Mississippi River, and that's going to be a really exciting lecture. And we'll cover groundwater and some of the specifics of our local groundwater here in Louisiana. And then we'll finally end that unit with glaciers and ice ages. And then finally, we'll get to the fourth unit of this class, which is really one of my favorites. It's on geologic time. All of the subjects from the previous units are really going to come back and shape the story of how the Earth formed and how it continues to change over time. We'll cover relative and absolute age dating, the age of the Earth, and we'll do a chronology of Earth history, starting at the beginning and going through all of the eons and eras of Earth history. So without, any further sort of background information, we're going to go into the regular material for the first lecture of this class. It's kind of a geologic overview and an emphasis on plate tectonics. It's going to be sort of your very first taste of plate tectonics. This is going to be a subject that keeps coming up again and again, and it's very, very important to the overall subject of geology. So the very first thing that you have to understand about geology is the importance of heat as a driver of all of the geologic processes. So whenever you get kind of lost in the details, whenever all of the sort of mundane stuff that we're going to have to kind of weed through gets to be a little too much, keep that as sort of your underlying mantra for this entire first unit of the class, that heat drives geology. So, internal heat on Earth is essentially what's responsible for all of the tectonic activity. If the interior of the Earth was not hot, then you wouldn't have this movement of the material in the interior of the Earth and plate tectonics and all of this reshaping of the surface that happens as a result through volcanic activity and mountain building and the formation of ocean floors. So essentially, you wouldn't have the Earth as a dynamic planet, or in other words, one that changes over time. If you did not have external heat from the sun driving some of these other geological processes, you wouldn't have things like rivers, you wouldn't have rainfall, you wouldn't have the formation of canyons and valleys and river deltas. So when you peel back all the layers and you look at the root cause of all the changes that the Earth goes through, heat is going to be very, very important. And we can really sort of divide this into two basic sources of heat, or the way the textbook refers to it is heat engines. And I always kind of liked that idea, so I ran with it, this idea that there are these separate heat engines that drive all of this geological activity. The first one that we're going to talk about is the more obvious of the two heat engines. As we stand on the surface of the Earth, it's going to be the surface changes that are going to be the most obvious and the most easily recognizable. So the external heat engine is basically just heat from the sun. The unequal heating of the Earth by the sun drives most of the surface geology on Earth. So what happens essentially is that the sun is heating the surface of the Earth, heating water, and driving water through the overall water cycle. So water evaporates out of the oceans. It moves up into the atmosphere because that water vapor is less dense than the dry components in the atmosphere. It condenses into the upper atmosphere, becomes larger particles, falls down as rain and snow, basic types of precipitation. And then that rain and snow is able to reshape the surface of the Earth. All that moving water and moving snow creates a great deal of erosion and essentially is part of the reshaping process of Earth and how it changes over time. Some of that water infiltrates into the groundwater system, but all of that water, whether it's flowing on the surface or through the groundwater system, ultimately makes its way back to the oceans. So it's the unequal heating of the surface of the Earth and the water cycle that's responsible for most of the superficial changes or the surface changes that the Earth goes through, or most of the surface geology. So most of these kind of changes, all the surface geology related to water, are all topics we're going to explore in the third unit of this class when we talk about rivers and groundwater, all that kind of good stuff. What we're going to concentrate on in the first unit is the internal heat of the Earth and how it is responsible for most of the forces that create uplift on the surface of the Earth, mountain building and volcanoes. So when we think about the Earth's internal heat engine, it becomes a little bit less clear and a little bit more abstract. The interior of the Earth is very hot, and this is part of what drives geology and drives all these processes that create uplift on the surface of the Earth. And that uplift allows for places where erosion can take place. So all of this uplift is really going to be just a side effect of the plate tectonic cycle. And the plate tectonic cycle is driven by the internal heat of the Earth. So this is the basic way that it works. The interior of the Earth is hot, and the closer to the core you get, the hotter and hotter and hotter that the Earth is. So the lower part of the core and the inner part of the mantle, so the lowest part of the mantle, the innermost core, the parts of the Earth that are closest to the very center of the Earth itself, those are going to be the parts of the Earth that are going to be the parts that are moving up towards the surface because of convection. So take, for instance, the mantle. The lowest part of the mantle is the hottest, and heat rises because it's less dense than the cold material. So all of that heat then rises up towards the surface of the Earth, and then that forces all this colder, denser material that was at the surface to move down to replace it. So most of the mantle is actually in a solid state. There are isolated parts of the mantle that are molten, but the reason for this molten part of the mantle is because of those isolated parts of the mantle that are hotter than others. So that's where the heat's rising and the cold sinking back down. That basic heat transfer process of hot stuff rising, cold stuff moving back down is called convection. So it's convection in the mantle that's driving all of the surface geology, that's splitting apart plates, that's causing the plates to move on the surface, causing plates to subduct under other plates, and all of these things that are related to plate tectonics that we're going to get into a little bit later. So the same thing's actually happening in the core. There's a part of the core that's in a molten state. It's liquid iron and nickel. And that molten part of the core, it's actually the outer core, is constantly convecting as well. And that convection creates something called the Earth's magnetic field. So we'll cover that in another lecture on the Earth's interior, the presence of the Earth's magnetic field and the result of that magnetic field to surface geology on Earth. So when we're looking for sort of a root cause of most of the geology that we see on Earth, like earthquakes and mountain building, the formation of the ocean floor, all of this is really related to the fact that the interior of the Earth is hot. If you're looking for something to sort of compare it to, an object that isn't hot in its interior, you don't really have to go very far away from the Earth to be able to find an object like that. The moon is a great example of an object that doesn't have molten parts of its mantle or core. It's basically completely frozen out from the surface all the way down to the core. And so because it's completely in a solid state, because it's completely cold, there is no convection. If there's no convection, there's no plate tectonics. And if there's no plate tectonics, then that object doesn't really change over time. There's also no atmosphere to speak of on the moon, or a very, very thin atmosphere made up of stuff like xenon that's not found in a great abundance. So because there's no atmosphere, there's also no surface geology. So the moon is sort of like a dead object compared to the Earth. The same thing would be true of the planet Mercury. That's a planet that doesn't really change over time. There's no plate tectonic cycle. There's no river formation. There's no canyons. And that's all because the interior of that planet is very cold, and there's basically no atmosphere to speak of. So lucky for us, we're not on a dead planet. We are on this dynamic, living planet that does change throughout time. And that's going to be a topic that we explore in a great amount of detail in this class. The first thing I just wanted to cover was this rationale of why those changes occur and the internal versus the external heat engine. Something else that I wanted to cover before we get into the broader plate tectonics theory is the basic structure of the interior of the Earth and the layers of the interior of the Earth that are going to be the most functional in the plate tectonic cycle. So inside the Earth, you could basically subdivide the Earth into crust, which is very, very thin compared to the other layers. It's essentially analogous to the skin on an apple. Underneath the crust, there's going to be the mantle, which is much, much thicker overall. And then underneath the mantle, getting closer and closer to the very center of the Earth, we have the core. Now, the crust and the mantle are more of a rocky combination than a metallic combination, mainly meaning there's a lot of silicon and oxygen in the structure of the minerals present that make up the crust and the mantle. So the crust is just a more lightweight type of rock than the composition of most of the mantle. Comparatively, though, the core is very, very dense, even compared to the mantle, and especially compared to the crust. The core is composed of nickel and iron. These are two very, very heavy elements, very densely found in the core of the Earth, both in the liquid part of the core, which is the outer core, and the solid part of the core, which is the inner core. We'll cover the basic structure of the Earth in a little bit more detail, and we'll get into the very, very important question of how we understand what these parts of the Earth that we've never been to are composed of in a later lecture, the fourth lecture that's called the Earth's Interior. For now, just keep in mind that it's crust, mantle, core. The crust is less dense than the mantle is less dense than the core. On the crust of the Earth, within this very, very thin overall part of the Earth, there are two basic types of crusts. There is a type of crust that we call continental crust, which is very, very thick, but very lightweight in comparison to the other type of crust, which is called the oceanic crust. The continental crust is going to be so lightweight in comparison to the composition of the oceanic crust that the comparison of the two is similar to the difference in density between water and air. It's really hard to appreciate that because most people just look at a rock and look at another rock and they could compare these two, and they don't really think that one is potentially twice or even maybe 3 times as dense as the other one, because compared to most man-made materials, both of those materials are going to be really, really dense. But the material that makes up the overall thickness of the continents themselves, or the part of the crust that's underlying the continents, is going to be far, far less dense than the material that makes up the oceanic crust. So that's going to be a really important concept going forward, because in plate boundaries, we're going to be looking at how these two different types of crust are going to interact with each other. And having one that's more dense than the other is going to be really important in figuring out which piece of crust is going to stay up on the Earth's surface and which one is going to sink down into the mantle or subduct. So we'll get into that in a little bit more detail in just a minute. I want to go ahead and throw out a couple of words for you that we're going to get into a lot more detail in the second unit of this class when we cover rocks and material and rocks and minerals. The continental crust is largely granitic or made up of a rock called granite. So this granite, again, is far, far less dense than the material that makes up the oceanic crust. It's basaltic, or a rock called basalt. Basalt is going to be 2, possibly even 3 times the density of granite. So again, the crust is very thick, but very buoyant, very low density. The oceanic crust is very, very thin in comparison, maybe something like 1/10 of the overall thickness that the thicker part of the continents is, but it's going to be very, very dense in comparison. Now, I'm going to go into a couple of other more sort of functional layers of the interior of the Earth. We've already covered the basic structure of the Earth, and this all still stands. It's crust, mantle, core. But when we talk about plate tectonics, we're going to be talking about lithosphere and asthenosphere. And the lithosphere is going to just essentially be the part of the Earth's crust and a little bit of the upper mantle that acts in a very brittle way. When exposed to a stress, like the stress of having the mantle be churning and overturning and driving apart plates, this crust and upper mantle is going to break. And that's all essentially that we mean by brittle, is that when it's exposed to stress, it's going to break instead of bend, instead of acting in a more ductile way. So it's kind of like a hard-boiled egg. If you take a hard-boiled egg and tap it against the counter, the shell will break, and the shell is fairly analogous to the lithosphere in plate tectonics. The underlying part doesn't ever really break, or at least not quite as easily, the egg white of a hard-boiled egg. It's a little bit more what we would call ductile. You would need a much greater stress to be able to break that part. So the rigid or brittle outer crust of the Earth is called the lithosphere. It's the first roughly 100 kilometers of the crust all the way down to part of the mantle. And then the part of the mantle that underlies the lithosphere is called the asthenosphere. And the word lithos literally comes from Greek to mean something that's made out of stone, or to imply something that is brittle, something that would be similar to a rock on the Earth's surface. Asthenos means something that's going to be a little bit softer or more like a plastic. So the asthenosphere is basically this layer of the Earth's interior that the brittle lithosphere is going to be able to sort of float on. So in plate tectonics, these pieces of lithosphere are going to be able to sort of move over the asthenosphere. Now that we've got all of these pieces of the game that are all important in their own way, we know the basic structure of the Earth is crust, mantle, core. We know that there are two different types of crust, the granitic continental crust and the basaltic oceanic crust that's much more dense than the continental crust. And we know that there's lithosphere, the crust in the uppermost mantle, and then asthenosphere, that softer plasticky layer that the lithosphere floats on. Now that we sort of have all of that under our belt, we can begin to understand what is happening in plate tectonics. This is very, very difficult to comprehend for most people because the plate tectonic cycle is extremely slow. But essentially what happens over time is that the brittle outer part of the Earth, the crust and the uppermost mantle, making up the lithosphere, is essentially in motion. These huge, huge pieces of the exterior of the Earth are in constant motion, sometimes moving away from other pieces, sometimes moving towards the other pieces or sliding past the other pieces. And when you see a boundary between one piece of lithosphere and another piece of lithosphere, and you see all of the stresses that that boundary is exposed to, you create essentially all kinds of different geological phenomenon where plates converge. You typically have mountain building, volcanic activity, deep earthquakes. When plates diverge, or plates move away from each other, you typically create mid-ocean ridges, you create new crust, and where the plates slide past each other, you just mainly have a lot of very, very sort of shallow stress that creates shallow earthquakes. So it's very easy to kind of picture and to be able to mark where all of these plate boundaries are. In later lectures, we'll get into the foundation of the plate tectonics theory, the origin of it, and the continental drift theory, how it evolved into plate tectonics, and really all the steps along the way, all of the proof that we needed to be able to believe that this is what was actually driving geology on Earth. Another really, really important point to go forward with is the idea that all geology on Earth is not local. It's not really limited to one particular point on the Earth's surface. All of the geology on Earth through the plate tectonics theory is basically interconnected. It means that the lack of earthquakes in South Louisiana is related to the same overall tectonic plate that is responsible for all of the very, very active part of the west coast of the United States. These two locations are essentially on the same tectonic plate, but the same thing that's actually creating all of this activity elsewhere on the West Coast is allowing for us to have a relatively tectonically docile experience here in South Louisiana. That when you really sort of stop and think of any particular location on Earth as part of the interconnected whole of the Earth, you can stop to appreciate how all of this geology is basically just a response of the plate tectonic cycle. So what I want to show you next is a really, really great little animation. I mean, it's not very high tech or anything, but essentially what we've done here is taken all of the continents on Earth and cut them out like little puzzle pieces and arranged them at the beginning of this little animation the way they would have been arranged 250 million years ago. At this point in the Earth's past, 250 million years ago, all of the continents on Earth were arranged together as one big supercontinent. And the name that we give that supercontinent was Pangaea. Pangaea began to split apart maybe 240 million years ago. As it continues to split apart, we create new oceans in the gaps. We split apart first North and South America from Europe and Africa, and eventually we split apart really sort of North and South America and start to create the Gulf of Mexico. So all of this happens incredibly slowly. So I know this is only like a 10-second animation, but this is happening over 250 million years. That's the amount of time it takes for a continent to move halfway around the globe. So if you kind of look at the actual rate in which this is happening, it's the same rate in which your fingernails typically grow. Something on the order of 1 inch per year, or 2.5 centimeters per year. So that's why it was so hard for such a long period of time for us to actually begin to accept the plate tectonics theory, because it happens incredibly slowly. It's not a process that we have a very easy time really sort of seeing in real time. There are very few geological processes that happen on the order of being fast enough to really sort of be appreciated by mere mortals like you and me. One of these processes, though, that is the direct result of plate tectonics is an earthquake. Earthquakes happen predominantly, not exclusively, but predominantly along plate boundaries. And every time an earthquake occurs, that's essentially just sort of this little shakeout in the whole plate tectonic cycle. This is the stress that builds up when one plate moves up against or sliding past another plate. And that stress is allowed to build up for hundreds and possibly even thousands of years before it's expressed all at once as in some cases, major earthquake. So you could see where most of the earthquakes that have ever been located and reported on Earth have happened, and most of them, the vast majority, coincide with plate boundaries. In fact, it's the reason why we know where the plate boundaries are located today. Without earthquakes, we wouldn't have as good of an idea of where to draw these boundaries on the geological map of the world, and an idea of sort of where we would go through and locate these plate boundaries. So, as you've already sort of begun to appreciate, it's the plate boundaries that are going to be very, very important in this first unit of the class. It's important to note that for us in South Louisiana, that means that we don't really have a lot of terribly exciting geology related to plate tectonics. I would argue that we do have in Louisiana very, very cool geology, worthy of being studied in a lot of detail, but most of it's related to groundwater, surface water, oil and gas, and it's all subjects that we're going to cover in a lot of detail in the third unit. In terms of plate boundaries, it's places like Southern California, the coast of Alaska, the Himalayas. These are going to be the really interesting geological places with regard to plate tectonics because they lie along the plate boundaries. So the next thing that we're going to talk about are these plate boundaries themselves and what kind of geology you can expect to see at each one of these plate boundaries. So the first type of plate boundary that we're going to go into is the type of boundary that forms when all of this heat in the mantle and all of this hot magma rises up towards the surface. The response of the lithosphere to all of this heat rising is that the lithosphere is going to split apart. And as that lithosphere splits apart, this rock from the mantle is going to come up and cool on the surface and solidify and replace it. So you can really think of plate tectonics as a recycling system for the crust of the Earth. And this is where the new stuff is going to come from. All of the new crust forms at divergent plate boundaries. The word divergent literally means to split. Like a road diverges into a wood. It splits into a wood into two paths. In plate tectonics, this is just going to be where the plates are going to move away from each other. Now, what's always happened to me in the past when I've taught this class, and I've been teaching this class for almost 10 years at this point, is the thing that everybody tends to think when they think about plates splitting apart is that there's going to be a gigantic canyon that extends down into the mantle, that there's going to be this huge void whenever you have plates splitting apart. But that's not sort of the natural way that the Earth works. whenever you split plates apart, all this magma that's going to come up from the mantle to cool and replace at the surface is going to actually create some of the higher points on the ocean floor. Occasionally, you can have this rifting occur or a divergent plate boundary originate on the continent itself. But after that plate boundaries continue to move for a while and the plates continue to split apart, that ends up being sort of the lower points on the surface of the Earth. So that ends up being the ocean floor. Essentially, new ocean floor is created at divergent plate boundaries. And these divergent plate boundaries almost always eventually turn into these things called mid-ocean ridges. The longest mid-ocean ridge in the entire world runs from almost the North Pole to the South Pole, almost, very nearly, and runs down the middle of the Atlantic. It's the main division that has continued to cycle, that split apart Pangaea 250 million years ago, and is continuing to push those continents further and further and further apart. There are certainly other divergent plate boundaries on Earth. I just wanted to use that one as an example because it's the world's longest divergent plate boundary, or mid-ocean ridge. So you can kind of get an idea of how this is going to work over time. The plate tectonic cycle almost works like bumper cars. These plates are going to continue to move around, occasionally allowing for all of these continents to all sort of pile up together as one big supercontinent. And then the heat that's generated underneath that supercontinent is going to create divergent plate boundaries and split apart the supercontinent over time. So whenever that happens, you get a divergent plate boundary that's seldom a straight line. It's usually a very jagged line, because it's very important to remember that all of this activity is going on not on a flat two-dimensional map, but on a spherical or roughly spherical object, which is the Earth itself. So let's take the mid-Atlantic ridge for an example. It's not this straight line running from north to south pole. It's jagged. It has lots and lots of offsets. And wherever you have offsets on a plate boundary, you're going to have this sliding motion where one plate is actually sliding past the other plate. So those types of plate boundaries are referred to as transform plate boundaries. Most of them are located on the ocean floor as part of an overall larger mid-ocean ridge. It's kind of like this. It has always tended to make sense to me. If I take my fingers and I interlace my fingers like this, and I pull my hands apart, the basic motion here is that my hands are diverging. But as my fingers slide past each other, each point where one finger slides past the next, that's a transform boundary. And that's very similar to what happens on the ocean floor, because that overall mid-ocean ridge is jagged and offset. So the main effect of these transform plate boundaries isn't to create some sort of tangible geological activity like a mid-ocean ridge or a mountain or a volcano, but to basically just get a lot of stress that's going to accumulate and be stored within these rocks to be released all at once as a shallow earthquake. Now, like I said, most of these are located on the ocean floor, but possibly the world's best known fault, one of the world's best known faults, is actually a fault located on one of these transform plate boundaries. The San Andreas Fault of Southern California is essentially a transform plate boundary. And I have a great animation here that shows you how that fault has really worked over time. It started out as this transform motion on an overall mid-ocean ridge, and then once that entire mid-ocean ridge was pulled underneath the continent along something called a subduction zone, which we'll learn about in just a minute, that became part of the continental motion as well. So really what's happening is that all of Southern California is essentially sliding down the coast. It's essentially everything to the west side of the San Andreas Fault is sliding comparatively to the other side. So that's always what you want to kind of keep thinking of with the transform plate boundary. It's this sliding motion. So far we have a divergent plate boundary, which is the plates moving apart, they're diverging. Sometimes you create a sliding motion along a broader divergent plate boundary. So the only thing left for us to cover is what happens when plates collide, when they converge, when they move towards each other. So at a convergent plate boundary, most of the tangible physical geologic features are going to be created, things like volcanoes and mountains. Now, when you're dealing with convergent plate boundaries, sometimes some of this crust is going to actually end up sinking back down into the mantle. This is the destructive part of the plate tectonic cycle. If at a divergent plate boundary you're creating new material, at a convergent plate boundary, that's where you're going to destroy material. So what happens in convergent plate boundaries is really ultimately going to depend on what types of plates are going to be involved. If you're dealing with oceanic and oceanic crust, so let's say both of these pieces of oceanic crust are meeting up together, or if oceanic crust is meeting with continental crust, then what's essentially going to happen is that one of these two pieces of crust, whichever one is denser, so in oceanic continental crust, it's obviously going to be the oceanic crust, and oceanic crust, it's going to be the denser of the two pieces of crust or lithosphere. What's going to happen is the denser of those two is going to sink down back into the mantle. So whichever one is less dense or light or buoyant, that is going to be the one that essentially wins at a convergent plate boundary. It's going to be the one that stays at the surface of the Earth, where the denser of the two is going to subduct into the mantle. So where the sinking of the crust occurs, that's called a subduction zone. And that sinking crust is going to be it's going to have a much lower melting temperature than most of the makeup of the mantle. And as such, as that material is pulled into the mantle, the first response of all this material is going to be to melt. As it melts, that molten material, that magma, is going to be lower in density than the rest of the mantle, so it's going to rise. And as that molten material ultimately makes its way up to the surface, it creates volcanic flows. All of that lava is going to flow out onto the surface of the Earth, and it creates volcanic structures over time. So volcanoes are not absolutely, but almost always going to be related to convergent plate boundaries. Sometimes you can have volcanic activity in the middle of a tectonic plate. You can have something called hotspot volcanism or intraplate volcanism. The Hawaiian Islands are one example of this, but that's going to be something that we're going to cover a little bit later on. For now, most volcanic activity is going to take place at convergent plate boundaries. The other thing that's going to happen at a convergent plate boundary, where one of the two or both of the pieces of lithosphere involved is going to be oceanic crust, is going to be that you create this very low point on the surface of the ocean, or the floor of the ocean, should I say, that you're going to create an oceanic trench where one plate subducts underneath the other. So as one is subducting under the other, that's going to be like a deep V on the ocean floor. It's going to be your low point. At divergent plate boundaries and mid-ocean ridges, that's going to essentially be your high point on the ocean floor. It's a little counterintuitive, and it takes some time to kind of appreciate why your convergent plate boundary is going to be marked by the low point and your divergent plate boundary is going to be marked by the high point. But it's a really important point to take home. So at oceanic continental or oceanic convergent plate boundaries, you typically have deep earthquakes where one plate is subducting under the other. You're going to have a lot of volcanic activity. And in some cases, with oceanic continental convergence, you're going to have small mountains forming on typically the edge of the continental crust. So for us in the United States, that would be the Sierra Nevadas, the Olympic Range, the far western mountains of the United States are all essentially formed at oceanic continental convergent plate boundaries. When you're dealing with continental convergence, this is the case where neither plate is going to subduct or be pulled back down into the mantle, because neither plate really can be pulled back down into the mantle. Both of these types of plates, both of these pieces of lithosphere are going to be so low density, so light in comparison to the makeup of the mantle that it would be kind of like trying to drag a balloon underwater or a beach ball underwater. Think about how difficult that is, how much energy you have to exert to take something like a beach ball and to drag it underwater. It's very difficult to do for exactly the same reason as you can't really subduct continental crust down into the mantle. It's just too light, too buoyant to be able to do that. So whenever continental crust meets continental crust, the only place left to go for all this material is going to be up. The highest mountains in the world, the Himalayan mountains, the Appalachian mountains, which are fairly sort of low elevation today, but at some point they rivaled even the Himalayan mountains. All of these are going to be created by continental convergence, because the only place left to go is to take all that material, pile it together, collide it together, it crumbles up. You have all these geologic structures that allow for all of this reduction in the overall width of the crust, and then all of this uplift that's eventually going to occur. So you get all of this mountain building. The highest mountains in the world don't typically have any volcanic activity. They're created through the collision of continents. So one great example of this is the formation of the Himalayan mountains. And I have a cool little animation that's going to show you the last roughly 60 million years of Earth history, preceding and including the formation of the Himalayan mountains. At some point, millions and millions of years ago, India was actually not connected to the rest of Asia. It was its own unconnected continental landmass. As the oceanic floor between India and the rest of Asia began to subduct underneath the Asian continent, it drags along India essentially as kind of like an item on a conveyor belt. So India continues to move closer and closer and closer to the rest of Asia and eventually collides. And once India collides with Asia, you don't see any more subduction of oceanic crust underneath Asia because that continental crust can't subduct. Instead, you see a lot of crumbling up of both pieces of continent and an extensive amount of uplift. And the Himalayan mountains, which include Mount Everest, those are the highest mountains in the world today. Partially because they're related to continental convergence, and probably even more importantly, because they are some of the youngest mountains that have formed today. So this all sort of brings me to the last point that I really wanted to make, and that's these opposing forces that are essentially the result of Earth's external and internal heat engine. They essentially work against each other. So Earth keeps changing, Earth keeps cycling in its dynamic, but these processes are essentially working against each other over time. The processes relating to the external heat engine, the sun, all of the processes including rain and snow and rivers and all of these things that drive erosion, are essentially bringing down the mountains. They are eroding down the surface of the Earth. All of these processes relating to the internal heat engine are creating all of this uplift. They're creating things like volcanic structures and mountains. So what we see on Earth is really sort of the result of these two opposing forces. And it's going to be the youngest features on the Earth's surface that are going to be the most impressive. The Grand Canyon only formed roughly 5 million years ago, which I know sounds like a really, really long time, but it's nothing compared to 4.5 billion years of Earth history. 5 million years ago is essentially just yesterday in geologic time. The Himalayan mountains are essentially still forming. In a sense, India is still slamming up into Asia. So all of these very, very young features are going to be the most impressive features on Earth. And some of the older features, like the Appalachian Mountains, they represent hundreds of millions of years of erosion over time. So, what I want to do next is take you on a little field trip that I'm hoping is really going to kind of solidify some of these ideas and give you a better idea of what all this really looks like in the real world. So, I hope you enjoy it. All right, today our field trip is going to be to the Grand Canyon. The Grand Canyon makes a wonderful spot to start on this first lecture for the class. It's probably the best known national park in our country. It's probably the greatest natural wonder of our country and one of the 7 natural wonders of the whole world. So geologists in particular really appreciate the Grand Canyon because unlike a lot of other places in the world, you get this wonderful exposure of a huge amount of Earth history. The Earth history that's exposed in the Grand Canyon ranges from the 2.5 billion year old basement rocks, as we call them. These are igneous and metamorphic rocks called the Vishnu basement rocks, all the way up to the very top of the canyon, up at those very, very top layers at the top wall of the canyon that are called the Paleozoic sedimentary rocks of the Grand Canyon. And those are 300 million years old. So the reason I'm telling you this is to kind of paint you a little bit of a picture of the difference between the age of the rocks of the canyon, which are really old, and the canyon itself. The canyon itself, which most people, think of, it's the most beautiful part of the Grand Canyon, it's actually relatively young. It's thought to be as young as only maybe 10 million years old. Another one of the natural wonders of the world, Mount Everest, is also extremely young compared to other geological features on the planet. And so what I hope you take away from this is this idea that these forces of uplift and erosion that shape our planet really create these amazing features that are actually relatively young, whereas older features on Earth have been heavily eroded and are not high mountains like Mount Everest or deep, deep canyons like the Grand Canyon. So I hope you enjoyed that. Until next time, keep rocking.